Why does a point traveling around a circle create a wave?
Science Makes Me Smile, presented by young Dr. JGC, a creation of old Dr. JGC.
How does circular motion create the familiar wiggling shape of a wave? I am young Dr. JGC. Let's begin. In the previous discussion, we explored the idea that frequency can be imagined as a point moving endlessly around a circle. But a fascinating question naturally follows. How does circular motion create the familiar wiggling shape of a wave? The answer is surprisingly simple. Imagine a point traveling smoothly around the edge of a circle at a constant speed. As it moves, its position is constantly changing. Sometimes it rises, sometimes it falls, sometimes it reaches a maximum height, and sometimes it passes through the center again. Now imagine shining a light on this rotating point and observing only its vertical shadow on a wall beside it. Although the point itself moves in a circle, its shadow does not move in a circle because we are observing only its vertical motion. Instead, the shadow moves up and down in a smooth repeating motion. If we record that up and down motion over time, the result is the familiar wavy pattern seen throughout nature. This wave is called a sinusoidal wave, and its shape comes directly from circular motion. What makes this idea so remarkable is that many physical systems behave exactly this way. Sound vibrations, radio transmissions, alternating electrical currents, ocean waves, light waves, vibrating strings. Even though these phenomena may appear very different, they often share the same hidden geometry, repeating motion that behaves like rotation around a circle. This is why the circle occupies such an important place in mathematics and physics. The circle is not merely a geometric shape, it is one of nature's most powerful generators of rhythm and repetition. The speed of the rotation determines the frequency of the wave. In other words, frequency measures how many complete cycles occur every second. A slowly rotating point produces only a few cycles per second and therefore a low frequency wave. A rapidly rotating point produces many cycles per second and therefore a high frequency wave. This difference matters because frequency is often connected to energy and power. In many physical systems, higher frequencies correspond to more energetic activity. A low-frequency sound may feel deep and calm, while extremely high-frequency vibrations can become intense, penetrating, or even destructive. Nature itself provides many examples. Powerful microwaves can heat matter rapidly. Intense ultraviolet radiation can damage living tissue. X-rays and gamma rays carry frequencies so high that prolonged exposure can become dangerous to the body. Even in sound, excessive vibration intensity can damage hearing. A gentle vibration may soothe us, while extreme oscillations can shatter glass, destabilize structures, or harm delicate systems. Thus, the number of cycles per second is not merely an abstract mathematical idea. Frequency often determines how much energy is being transferred and how powerfully a system interacts with the world around it. So beneath the smooth rise and fall of waves lies a beautifully simple idea, a point endlessly traveling around a circle, casting a rhythmic shadow through time.
Now you see why frequency is the hidden rhythm behind motion, energy, and many repeating patterns in nature. Fascinating, isn't it? Let me know your thoughts in the comments. And as always, thanks for watching Science Makes Me Smile.